Preparation methods of alkenes. First, from alkyne. Alkynes we know triply bonded compound, carbon-carbon triple bonded compounds. Alkynes can be converted to alkenes, means doubly bonded carbon, by breaking one of the pi bond by the adding hydrogen. This reaction is called hydrogenation reaction because it involves addition of hydrogen into one pi bond of alkyne. This reaction, hydrogenation reaction, takes place in the presence of a catalyst. Hence, it is also called catalytic hydrogenation. Catalytic hydrogenation of alkynes to get alkene should be done carefully because calculated amount of hydrogen only we need to take in the reaction, and the catalyst should not be highly active. If the catalyst is highly active and if there is excess amount of hydrogen gas, what happens? Both of the pi bonds of the alkyne break, and the product will be not alkene but alkane, single bonded compound. So in order to stop the hydrogenation reaction in the formation of alkene, this catalytic activity of the catalyst should be reduced. Partially deactivated catalyst is used. For example, the catalyst used here is palladized charcoal. Palladium added charcoal. Palladized charcoal. Charcoal we know a form of carbon. Palladized charcoal, its activity, catalytic activity has to be reduced by adding some poison substances which reduce the activity are called poisons. Examples of poisonous substances are sulfur compounds or quinoline. So partially deactivated, palladized charcoal partially deactivated by adding sulfur compounds or quinoline. These are called poisons. Quinoline or sulfur compounds are added to palladized charcoal in order to reduce its catalytic activity so that we can stop the reaction in the alkene stage. It will not proceed further to form alkene. Only one of the pi bond only we need to break. So calculated amount of hydrogen is added to an alkyne. For example, ethyne. CH triple bond CH. We know this is ethyne. Hydrogenation in the presence of partially deactivated palladized charcoal. This catalyst has got a name. This is known as Lindlar's catalyst. What is Lindlar's catalyst? Partially deactivated palladized charcoal. Catalyst is called the Lindlar's catalyst. So only one of the pi bond only break and hydrogen will be added to the triply bonded carbon atom. So what do we get? CH2 double bond, triple bond breaks into double bond, then CH2. We get ethene. Then another catalyst used in the same process is sodium. Instead of Lindlar's catalyst, we can use another catalyst, sodium in liquid ammonia. Sodium in liquid ammonia is another hydrogenation catalyst. In the presence of this catalyst also, hydrogenation of ethyne will give the same product. And in the case of alkenes, product alkenes which can show geometrical isomerism, that is cis-trans isomerism, if possible in the alkene, the Lindlar's catalyst give cis-alkene. Sodium in liquid ammonia. In the presence of catalyst sodium in liquid ammonia, trans alkenes are produced. Because ethene do not show cis-trans isomerism. Here there is no difference. But in the case of alkene product where cis-trans isomerism is possible, with the Lindlar's catalyst, hydrogenation reaction gives cis isomer. With the sodium in liquid ammonia, we get a trans isomer. Clear? Let's take an example. We take CH3, C triple bond, C, CH3. This is the compound. This is but 2-ine, but-2-ine with the Lindlar's catalyst, that is palladized charcoal, partially deactivated palladized charcoal. What happens? Addition of hydrogen. one pi bond breaks into the triply bonded carbon atom, one hydrogen atoms added. So what do we get the product? CH3, CH, double bond, CH, CH3. See, this alkene can exhibit cis trans isomerism because it contains identical groups on the doubly bonded carbon atom. With the palladized charcoal, the isomer obtained will be cis isomer. Cis isomer means identical groups on the same side. So hydrogen atoms on the same side, methyl groups on the same side of the double bond. You get cis isomer of the alkene. Cis alkene is the product. Now the same reaction, if carried out in the presence of sodium in liquid ammonia, what they say, we get trans isomer. Trans isomer means same product but different spatial arrangement. How the difference in the arrangement? Hydrogen atoms are on the opposite side, CH3 groups are on the opposite side. Same reaction, but here we get trans alkene. Trans isomer is the product with sodium in liquid ammonia. So partial reduction or partial hydrogenation of alkynes gives alkene. This is the one of the method to prepare alkene from alkyne. Now, second method to prepare alkene, that is from alkenes can be made from alkyl halides. Alkyl halides means in alkene one hydrogen atom replaced by halogen. For example, if you take CH3, CH2, Br. So one bromine, halogen atom bromine attached to an alkane. Hydrogen atom of an alkane replaced by bromine atom. So this is ethyl bromide or bromoethane. The name of the compound is bromoethane. Alkyl halides, when heated with alcoholic potash, it is heated with alcoholic potash. What is potash? Potassium hydroxide. Alcoholic potassium hydroxide. What happens? Here the bromine atom attached to carbon atom. Bromine is the functional group here. Functional group attached to carbon atom we name in organic compounds. Functional group directly attached to carbon atom is named as alpha. And the adjacent carbon, next carbon, is called beta. So this is alpha carbon atom, this is beta carbon atom. So during this reaction, carbon-bromine bond breaks and bromine leaves the reaction. This manner. Bromine is eliminated from the alpha carbon atom and one of the hydrogen from the beta carbon atom also eliminated. So here I am showing one of the hydrogen atoms separate. One of the hydrogen atom, this is the beta hydrogen because this hydrogen atom is present in the beta carbon atom. So here one of the hydrogen atom eliminate from the beta carbon atom. And what do we get? What will be eliminated here? A molecule of HBr will be eliminated. Hydrogen from the beta carbon, halogen, here bromine from the alpha carbon atom is eliminated as minus HBr, hydrogen bromide. So what do we get? Here two bonds break, right? So here this pair of electron will be taken by bromine. So bromine will be leave the reaction as bromide ion, but this hydrogen leave the reaction without taking its electron pair. So this pair of electrons are free now. So this would make a new bond here. So what do we get the product? The product obtained will be CH2. One of the hydrogen has been eliminated as HBr. CH2 double bond CH2 plus HBr. Clear? Since there is elimination of hydrogen and a halogen, this reaction is called dehydrohalogenation reaction. Dehydrohalogenation reaction. This reaction is also known as beta elimination reaction because beta hydrogen atom is eliminated. Also known as beta elimination. Why beta elimination reaction? Because the hydrogen atom from beta carbon atom is eliminated. So halogen from alpha carbon, hydrogen from beta carbon is eliminated as hydrogen halide. We get the alkene as the product. This reaction is important because we need this reaction next year also. We'll study in detail about this reaction in +2. The reactivity of various halogens, if you compare, for example, fluorine, chlorine, bromine, iodine. The reactivity of halogens, if you compare towards this reaction, iodides are more reactive than bromides. Iodides are more reactive than chlorides, which are more reactive than bromides, and fluorides are least reactive. This is the order of reactivity of halogens towards this reaction, towards beta elimination reaction, because this bond needs to be broken. No, so if iodine is the halogen present, carbon iodine bond is very weak. Iodine is larger in size, less electronegativity, so this bond breaks very easily if iodine is present. But if fluorine is present, the bond is very strong, so difficult to break. Fluorides are less reactive, but iodides are most reactive towards beta elimination reaction. And when you compare the reactivity of various alkyl halides, primary, secondary, tertiary, the order of reactivity is found to be tertiary more reactive than secondary than primary. We will study in detail why this order told in +2. So this is the second method to prepare alkene. Alkene can be made from alkyl halide by dehydrohalogenation reaction or beta elimination reaction. Now the third method, alkenes can be made from vicinal dihalides. Vicinal dihalides. Dihalides means we know 2 halogen atom. Dihalides means 2 halogens. If both the halogens are same, and if they are present on adjacent carbon atom, if both the halogens are, say, chlorine, and if they are present on adjacent carbon atom, like this, CH2Cl, CH2Cl, right? This is called a vicinal dihalide. Vicinal dihalide means dihalides with the same halogen atom on adjacent carbon. If both the same halogen atoms if present on adjacent carbon atom, the type of dihalide is called vicinal. So this is a vicinal dichloride. Vicinal dihalides, when treated with zinc, what happens? This carbon chlorine bond breaks. This chlorine atoms make bond with zinc and form zinc chloride. Zinc chloride will be formed. And what happens here? Here a double bond is produced. CH2 double bond CH2. We get ethene. So vicinal dihalides, when heated with zinc metal, we get alkene. Similarly, one more example, CH3 CHBr, CH2Br. Another vicinal halide, no, 2 bromine atoms on adjacent carbon atom. When heated with zinc, what happens? Zinc bromide will be eliminated, and here after the elimination of these 2 bonds, what happens? Here a double bond will be produced. That is CH3 CH double bond CH2. We get propene plus zinc bromide Br2 will be formed. Now the last method to prepare alkene, that's from alcohol. Alcohols can be converted to from alcohols. Alcohols can be converted to alkene. Take the example of ethanol. CH3 CH2 OH. This is ethanol. Alcohols contain the functional group OH group. Here when it is heated with concentrated sulfuric acid. Here concentrated sulfuric acid acts as the catalyst. When it is heated with concentrated sulfuric acid, what happens? A molecule of water will be eliminated. How? The OH group, this functional group attached to carbon atom will be named as alpha, as we told in the alkyl halide. Here the functional group is OH group. OH directly attached to carbon atom is named as alpha. The next carbon atom is named as beta. So OH group will be eliminated from alpha carbon, and one of the hydrogen atom from the beta carbon, CH2H, one of the hydrogen atom from the beta carbon. These two will be eliminated together. These two will be eliminated as a molecule of water, H2O. So what happened here? A double bond will be produced. CH2 double bond CH2. See, actually the mechanism involved, this carbon oxygen atom is more electronegative, you know. So what happened? This bond break heterolytically. Oxygen take away with the electron pair. This carbon atom become positive. So this carbon atom will take the one of the hydrogen atom shared with the adjacent beta carbon atom will be removed. One of the bond shared with the beta hydrogen atom will be taken by this carbon and they remove this hydrogen as without electron. So this OH minus and this H plus combine and form water molecule, and here a double bond will be produced. Since beta hydrogen atom is eliminated, this is also an example of beta elimination reaction as in the previous case. So here a molecule of water is eliminated, hence this reaction is called dehydration reaction. Dehydration means removal of water. This reaction takes place in the presence of catalyst, acid catalyst. So this is also known as acid catalyzed dehydration reaction. Acid catalyzed dehydration of alcohols gives alkene. This reaction also, including its mechanism, we will study next year. So these are the methods to prepare alkene.